In the previous video, we saw that for the boundary value problem y double prime plus lambda y equals 0 and boundary conditions y of 0 equals 0 and y of L equals 0, eigenvalues are lambda sub n equals n squared pi squared over L squared for positive integer values of n, and eigenfunctions are y sub n of x equals the sine of n pi over L x. We're going to put these into the context of physical situations. Suppose we have some road, a stretch of road, and a compressive force of P is being applied to one end of the road. Could be the road is getting hot, it's expanding, and it's butting up against an immovable object there. And so it's feeling a compressive force, if roads can feel, on one end. Or a vertical column that has a compressive force on the top of it, of P. Now, of course, if you put a compressive force on the top of a column, then the force is going to be visited on both ends of the column, but we're just saying it's not being compressed from both ends. For these scenarios, we're going to say the length of the road is L, or the length of the column is L. Yeah, it's the same L that we see in the eigenvalues and eigenfunctions. I know, this is a lot of text. Consider a vertical beam of length L with a load P applied to one end, or a road with a compressive force P applied to one end. Theory of elasticity provides the differential equation EI d2y dt2 equals negative py, or EI equals d2y dt2 plus py equals 0. If we solve for EI, we have an equation of the form that we were just talking about. Second derivative of y plus p over EIy is equal to 0. EI is called the flexural rigidity of the beam. E is Young's modulus of elasticity, and I is the moment of inertia of a cross-section of the beam. That's the shape's inherent resistance to bending. If you want to dig deeper in this, theory of elasticity is where to go. Considering P of x equals 0 and Q of x equals 1, and letting lambda equal P over EI, this has the form y double prime plus lambda y equals 0, the same equation that we've been analyzing in this set of videos. So using that substitution, lambda equals P over EI, and considering boundary conditions y of 0 equals 0 and y of L is equal to 0, now I'm going to pause this for a moment to go back to our little drawing here. Y of 0 equals 0 would be an equilibrium height, we'll call it, on the left, and y of L equals 0 would be an equilibrium height on the right. Likewise, the vertical beam. This is why I think boundary conditions makes sense. I was mid-sentence here. We're going to have solutions y equals b times the sine of n pi over L x. Now we've been talking about these eigenvalues, right? This eigenvalue, lambda sub n equals n squared pi squared over L squared, is a value for which the solution to the differential equation is not the trivial solution. In other words, we're talking about a situation where the beam, or I guess this one's the road, or the beam is not flat. This is a situation in which the road or the beam will buckle, also referred to as deflecting. So the column or the road is going to buckle or deflect if P, the force on one end of it, is equal to n squared pi squared EI over L squared. That's due to the substitution that I circled up here. When n is equal to 1, we have what's called the first buckling load. Now, suppose we restrain or support the system halfway across its length at L over 2. Then taking that L over 2 and putting it in the denominator here, in place of L squared, is going to give us a P that is 4 times as big as the previous P when N was 1. You can see where N squared is, I've now written a 4. This corresponds to N equals 2, and this will be the smallest critical or buckling load. I know this is kind of a lot here, but let's go back. When N is equal to 1, we said we had the first buckling load. And we're talking about a non-trivial solution to the differential equation, so not just y equals 0. Then we have the beam buckling. That's called a deflection curve. What we just saw is if we support the column halfway up, right, at L over 2, then we can apply 4 times P to that column. When it buckles, since it's restrained, it's going to be more of like an S shape. Now this is an exaggerated view of how it's going to buckle, but this is basically what's going on. These are intended to help you understand what's going on with an eigenvalue and an eigenfunction and what it means to have a non-trivial solution. We're now going to shift gears and consider a beam that's going to be either supported or embedded. We're going to shift gears now and consider what can happen with a beam. For what we're considering right now, we don't have a compressive force applied to the beam or anything. This is just a beam that's going to end up sagging under its own weight. Say it's supported on the ends, and it's got some mass, and so it deflects. We're going to examine a differential equation, actually, that describes what's happening with the beam, and then the solution of the differential equation is going to be what's called a deflection curve. The scenarios we're going to consider are this beam is embedded at both ends and sagging in the middle, or as a cantilevered beam embedded at one end and just hanging on the other end. That could be like a diving board, or in the case of a vertical situation, a tall building is actually a cantilever. And finally, we could have a beam that is simply supported at both ends. It's not embedded. I mean, it could be hinged, connected in some way, but not in such a way, it's not a rigid connection. All right, so this is going to be another text-heavy thing, but we'll get past it here. If we've got a beam of length L, the bending moment is the response or resistance to load. It's denoted by m of x, and it's related to the load per unit length, so just the weight of the beam itself. By second derivative of the moment is equal to w of x, that load per unit length. Again, theory of elasticity. Assuming down is positive, m of x, the moment, is equal to EI times kappa. That EI is a constant of proportionality. Kappa is the curvature of the elastic curve. Even if you haven't seen multivariable calculus, curvature is just how bendy a curve is. And we can understand this formula here, y double prime divided by 1 plus y prime squared denominator to the 3/2. Okay, but good news. We're considering small deflections. So y prime is basically 0. We don't have to worry about that denominator. So we get that m, the moment or the resistance to load, is EI y double prime. We had that m double prime was equal to w of x. So differentiating m equals EI y double prime twice is going to give us EI times the fourth derivative of y is equal to wx. Now, this becomes the starting point for our work. Here we have our fourth order differential equation. And then our boundary conditions are going to be related to whether a board is embedded or free or simply supported at one end or the other. The input values for the independent variable are 0 and L being the length of the beam. For the deflection curve, Y prime is the slope of the curve. And we can see when the beam is embedded at both ends, or embedded at one end, I'll just focus on, y prime is equal to 0. If it's embedded here, y prime is 0. And if it's simply supported, y prime is not 0. So these are unique to being embedded. Let's continue. Y double prime is the bending moment. That's the m that we were talking about before. And then Y triple prime is what's called a shear force. A shear force results from a beam that is sagging, having its top compressed inward and the bottom stretched outward. Because these compressive and tension arrows are pointing opposite direction, they're causing what's called the shearing force. That's a great visual of what a shearing force is. The way these relate to boundary conditions is if an end of the beam is embedded, y is equal to 0 and y prime is equal to 0. If the end of the beam is free, then y double prime is equal to 0 and y triple prime is equal to 0. If the end of the beam is simply supported or hinged, then y at that end is 0 and y double prime at that end is 0.